Hey guys, in this tutorial we're going to take a look at using parametric equations to define shapes and how we can use those parametric equations to do more complex things in Grasshopper. So for starters, what is a parametric equation? Basically it's an equation which is split up into an x component and a y component so that we can evaluate the x and y and possibly even z values of that function all separately in order to create a shape. Alright, so we're going to start with a brand new definition. And so what we're going to use is the expression editor. We're also, okay, and so we'll start off by setting up our definition. So in order to do this, I'm just going to use some custom variable names, and I'm going to use r for my radius. I'm going to use t for my parameter value. And so what we can do is we can start off with a range component, and we're going to make that we're going to make the domain a multiple of pi. And so I'm just going to set my slider to a maximum of 2, and I'm going to bring in a domain component. So by default, the start is 0. I'm going to set the maximum to the slider, which is going to be set to 2 pi for now. I'm going to plug that into my domain, and we also need a number of values. So I'm going to chuck this to 360 just for convenience sake, and we're going to plug that into our t value. Our t value is our parameter value at which we're evaluating some sort of expression. And so our expression is going to be r times cosine open parentheses t close parentheses. R here is our radius, and so I'm just going to set this to a value of maybe 10, or maybe make it 100. Okay, so now what we did before when we were using sign expressions was we plugged our range value into the x, and we plugged this into our, oh, hold on, that's throwing an error at the moment just because I haven't set my steps. So I'm going to set that all the way up to 360. Alright, so we'll go into top view for now. And so you can see straight off the bat we've just generated a sine curve like we did in the previous tutorial. Now what we can do instead here, because what we did firstly was we just plugged in our range value straight into the x, but we could also plug another equation into the y. So we'll for this we're gonna make the second equation r times sine of t. So this will be my x equation, and this will be my y equation. And what you'll notice, what you should notice, is that we get a circle. If I just create an interpolate curve through here and turn this off, oh, wrong one. So this is the equation of a circle. The x component is r times cosine t, and the y component is r times sine t. And like we did before, we can, if we shift through the slider, we can find any range that we want. And this is also a really good way to show you how pi and radians work. If I were to just set some snapping values here to 0.5, 1, and 1.5. Okay, so we can see if I set my slider to 0.5, that's 0.5 times pi. So that's pi over 2 radians, which gives us 90 degrees. 1 times pi makes pi radians, which gives us 180 degrees of the circle. 1.5 times pi, 3/4 of the circle, or 270 degrees, and 2 pi makes 360 degrees, or an entire circle. Now what else could we do with this sort of formula or system? We could make a spiral. So how do we do that? We'll just we'll copy this, and instead of using r for my radius, I'm going to use t for my radius. And I'll just actually copy and paste all of this. Plug that into my t. We don't need an r at the moment, but we can just leave that there. And I'm going to set my max value for this to some arbitrary number like 24. If we go into perspective, you can see we've now got this spiral. And so basically what we're getting is we're just taking a circle, but instead of giving it a uniform radius, we're giving it a slightly increasing radius with every single step between 0 and 2 pi. So now we could keep this going, and we could increase this factor to keep giving us a larger and larger spiral as far as we could possibly want to go. Furthermore, I could also plug in a z value. In fact, we could just plug in our range value into the z, and there we go. Now we get a spiral which not only stays flat but ascends. Now, alright, we'll look at one more curve equation. This is a pretty cool one. I came across this in maths class a while back. This is a heart-shaped curve, and if we go on the Wolfram Alpha webpage, you can see it actually gives us an equation for the x and y components of this curve, meaning that we can make it in Grasshopper. So we'll give that a try. I'll make a copy of all of this. We'll turn all of these off, and we'll turn them off, my bad, and we'll go back to our top view. Alright, so for this one, we're going to type in 16 times sine t, and if we look at the formula, it was sine cubed of t. And so the way we represent sine cubed t is by putting the sine and everything along with it in brackets, raising it to the third power, and then closing that off. So that's the first part of our equation, and then the second part is a bit more complex. So it's 13 times cosine of t minus 5 times cosine of 2 times t, I believe, minus, yes, 5 times cosine of 2t minus 2 times cosine of 3 times t minus 4 times cosine of, cosine of 4 times t. And there we go. There is our heart shape, just as simple as that. So basically any equation that you can find in this form, you can plug into here and we'll just be able to see it in Grasshopper. Alright, now let's take this a step further, and we're going to look at how we can generate a three-dimensional shape. Take this, maybe do I need to copy it? Okay. Well, for this we'll be generating a sphere. So in order to generate the sphere, it's pretty simple. We'll start, actually let me copy and paste this first section because that's the circle. So in order to generate a three-dimensional, a sphere is basically a circle which has been revolved a certain angle in order to create a three-dimensional shape. And so in order to do that, we need we need more than a one-dimensional parameter value. We need a two-dimensional parameter value. And so for that, we're going to use u and v. Same thing here, u and v. And so we'll set this to r times cosine u, r times sine u. Okay. And we'll just turn our points on. And so we need another one of these because we need those two dimensions, or those two dimensions of values, and we also need a cross-reference component. This is so that we get for every value of u, we get a corresponding value of v. and 360 is way too much for this. I'm going to take them both down to 24. Okay, and so now we're going to plug in our U and V and our U and V. Okay, and so right off the bat, this is not going to work, because what we need to do in order to turn this into a three-dimensional shape is we need to find a way to essentially revolve this around an axis. And the way we do that is by adding, we need to add something extra to the function. So what we add is a multiplication of cosine V to the x, multiplication of cosine V to the y, and then the z value is r times sine v, and we'll plug that in. And now you can see we get our three-dimensional sphere, and we can no longer do an interpolate curve through that because it doesn't really make sense. So for this we need to use a surface. So we're going to use a surface from points. And we need a u value. And so if you remember, anytime we're using a range component, the number of steps, we're going to need to add 1 to the number of steps in order to create, or in order to give it the correct number. So we're going to just add an expression for u plus 1. I'll plug that in here, and I'll change this to u. And then when we plug this in, well, okay, you might think, okay, sure, we've got a sphere, but we're not quite there yet, because we have the wrong bounds for the setup over here. The correct setup for this is, oh yeah, so basically this original part of the equation is the bounds in which the sphere or the shape will be created, or for which the equation holds true. So for a circle, the equation is within the bounds 0 to 2 pi. Same with the heart shape that we created. But the where is it now? The sphere needs a slightly different configuration. So the U domain is from negative pi to pi, I believe, and we need to remove the 2, and then our V dimension is between negative pi over 2. Let's see, where's my negative? I'll just make a copy of that. Oops, accidentally plugged that in there. So it's from negative pi over 2 to pi over 2. And so there we go. We have now got a correct sphere, which has been evaluated parametrically. And so now what we could do with this is we could chuck in a slider over here into our beginning value, and we can basically change the domain for which we want this to occur. So this is a really good way to just trim a sphere, because all we need to do is just change the evaluation bounds. We can change this one. We could also change this one. And I think that's just a really neat way to understand how the parametric equation works. Okay, now what we're going to do is we're going to create the same three-dimensional, we're going to turn our heart shape into a three-dimensional shape as well. So for that we need all of this, and this. Okay. And so we'll copy that down here. And so similarly like we did for the circle, we're going to multiply our x equation by cosine v. And we also need to change this to u, and then add in our u and v parameters. We'll do that over here as well. So u and v, and automatically you're going to notice it's going to throw an error because, well, over here we haven't given it a v value yet, and over here we still have t value. So I'm going to quickly change all of these over to u's. And we're going to take all of this, and we're also going to multiply it by cosine v. Oops, I don't quite like that in capitals. And just stop typing for some reason, that was weird. Turn caps lock off, cosine of v. And similarly to our sphere, we just need to add a z function, which is going to be sine of v. And I'm also going to plug in a radius value into that. Okay, now we need to plug in our u and our v values. So we're going to make a copy of this again. We're going to take these numbers way down to 24 in each direction. And we're going to cross-reference them. So there's our u, u, and u, v, v, and v. Okay, and then once again, we need our surface. Oh. And I'm just going to make a copy of this and plug this in here. Okay, so off the bat it's doing something a bit weird. We'll turn our points on and see what's going on. Okay. I see what the problem is. We've not set our bounds correctly. So we'll just go 2 to 2 for now. Nope, not quite. We need to set this. You know what we can do? We can copy and paste this, which we created over here. So we need that and that, along with our domain. You know what? Let's just copy all of this. Get rid of this. And let's reconnect up our u and v. And so there you go. You can kind of see it working at the moment. And there we go. Now that we've corrected the bounds, see, I just needed to set the right bounds for that to work. And so that was from negative pi to pi, and our v domain was from negative pi over 2 to pi over 2. And so what this basically does is it revolves the original heart shape that we created around an axis, which is this y-axis here, and it creates a shape. So now as we adjust our variable r, we can create a more inflated or deflated heart shape. And I'll just bake that. I can also swap these around if you maybe wanted to see it face on as opposed to face up. So I'll swap this and this, and there you go. There's the heart shape looking a bit more proper. We can bake that out, have a look, and there you go, nice three-dimensional heart. It does have, the edges on it are a bit hard, so what we could do in Rhino is we could just take a rebuild function, and you know what, I'll just keep those point count values at 12 and 12, and there you go, it reconstructs the heart shape in a quite a nice way, I'll be honest. Yeah, I quite like that. There we go. So that's how we create our heart shape. Now we're going to look at one more kind of parametric equation, and that is for the Mobius strips. The Mobius strip is a really interesting mathematical concept because it's a surface which turns on itself, meaning that if you could walk around this surface, you would cross both sides of that surface, but you would never notice it just by walking across it. So let's try and bring that in. We'll have a look at what Wikipedia tells us the equation is. So here we go. It's given us the x, y, and z equations for this. We're going to go ahead and type these in. I'll copy all of this, and we'll get started. So our x equation is 1 plus, in bracket, open parentheses, 1 plus, open bracket, v over 2 times cosine u over 2 times cosine of u. And it's giving us an error. We'll find out why in a sec. It's probably because I forgot to close this parentheses over here. Okay, there we go. No syntax detected. Now I'll do the next one. The next one is 1 plus, once again, v over 2. Oops, let me just check that in brackets. Times cosine u over 2. Oops, not cosine d, cosine u. We'll close the parentheses there again and then multiply by sine of u. There we go. And now our z equation is v over 2, sorry, let me put that in parentheses, times sine of u over 2. And there we go, let me just hook those up properly. So now what we should have is our Mobius strip. We can also multiply that by r in the front. Okay, so there we go. There is our piece of geometry. Now, in order to explain how the Mobius strip works, I'm just going to go and, instead of using a surface grid, instead of using a surface from points, I'm going to use a mesh from points. You're going to see what exactly happens here. So we'll plug our point value in. We've got our u parameter. We also need our v. So we'll do v plus 1. You don't need to change these from u and v. I just do because I like my definition to be a bit tidier. So we'll plug our u in and we'll plug our v in. And so there we go. There's our mesh representation of the Mobius strip. So when we bake this out, you're not going to see too much of an issue apart from this seam over here. And so this is where basically the front of the surface connects to the back of the surface. And the way we can visualize this is using a face normal component. This will show us the normal direction of each mesh face. And we'll get a vector display. And so that's our anchor and that's our normal. And so we'll just turn that off, and you can see on this side the faces are pointing inwards, and as we track that around, they're pointing inwards, a bit of a slip of the tongue there. And then once we get to about here, the direction of the surface changes, and suddenly the faces are pointing outwards up until we get to this seam point here, where you can see the direction changes, where it goes from facing outwards to facing inwards. And so this can be really tricky to deal with in geometry. At the moment it's not too much of a problem, but if we were to weld these mesh vertices together, you'll see a bit of a problem. As soon as I bake this out, we get this black line over here. And so you get this black line anytime the normals of your face don't match up properly, where we've got these outwards facing as opposed to these inward facing vertices. It really, like, Rhino doesn't know how to deal with this. You could, if you wanted to, take this into another program like 3ds Max or Maya, because they do have the ability to force an object to be double-sided, but that's not the issue here. Basically, you should just this was just an interesting sort of equation that we looked at, which I thought I'd bring up just to show you some issues that can arise with the mesh, as well as how to construct these parametric equations. So that was a bit of a tangent, but anyway, hope this has been an interesting tutorial. We've looked at using parametric equations to form both curved geometry and surface or mesh geometry, and we've looked at how you can use those parametric equations and plug them in to get a result. And so basically, anytime you've got equations that come in this form, you can chuck them into Grasshopper and see what your result will be. So yeah, have fun with it.